All right, now we're going to take a look at Kepler's third law, which is this equation given right here that lets us figure out distances and orbital times, meaning a planet's year, based on other planetary data. So we're always, when we're dealing with the solar system, we're going to deal with Earth distances and Earth years. So we'll always say that R1 is 1 AU for Earth. And remember, that's 93 million miles. And remember that T1 is 1 year. So we're always going to measure things in terms of AUs and years. So for example, Jupiter's 5.2 AUs from the Sun. We want to know how long it takes to make one revolution. All right, so I'm going to set up my formula. R1 cubed over T1 squared equals R2 cubed over T2 squared. And what we're going to do is, let me just actually move this over here so we have it. So working with that, let's go ahead and actually put in our numbers here. So I've got 1 for Earth cubed, that's 1 AU cubed, over 1 year squared equals 5.2 AU cubed for Jupiter over its year squared. I'm going to multiply, so this is just 1, so I can actually simplify this and just say 1 equals 5.2 cubed over T2 squared. That's for Jupiter. I'm going to multiply both sides by T2, so that's going or T2 squared. So that's going to be T2 equals 5.2 cubed. And then I'm just going to multiply this out. So 5.2 cubed is 141. I'm just rounding here. So Jupiter's year is going to be the square root of 141, which is going to be in Earth years. So for every year that Earth takes, Jupiter is going to take about 11.9 years. So about 12 years for Jupiter. All right. Now we're going to do a little bit of a different problem. Oh, Pleppers. I don't know what that is. I think it was just me typing something weird. So let's just get rid of that. So for problem 2, again, we're going to use the same setup here. So I'm going to actually take this formula and write it here. And I'm going to kind of simplify my work and just kind of note that since R cubed over T squared for Earth is just 1, I'm going to here just write a big old 1, okay, just kind of borrowing that idea, equals Neptune's distance cubed over 164.8 squared. I'm going to simplify this fraction further and write 1 equals R2 cubed over 164.8 squared. So that's 27,159. I'll just leave the decimal out. It's not going to affect the answer too much. And I'm going to multiply both sides by this number here. So that'll cancel that. And so what we'll need to do is to get R2, that's going to be the cube root of 27,159. Or I could take 27,159 to the 1/3 power. Either one of those would work. But the point is, I'm getting that Neptune is about 30 AU from the Sun. So 30 times the Earth-Moon distance, or Earth sun distance. By the way, since it takes 8 minutes for light to get from Earth, since it takes 8 minutes for light to get from the sun to the Earth, it means it's going to take about 240 minutes, or about 4 hours, for light to reach Neptune from the sun. But we did that in the last unit. All right, now we're going to do a couple problems with escape velocity. This is the speed you need to be able to launch a rocket off a planet and basically not have it eventually stop and crash back into the planet. It can actually break free. So this is the radius of the planet itself. This is its mass, and this is the number g. So to get the escape velocity, we're going to take 2 times 6.67 times 10 to the negative 11th. That's for the g. We'll times that by m, which is 5 times 10 to the 20th. And then we're going to divide by r, which is 300,000. All of this under a square root. And when we actually simplify that, we're going to get an escape velocity of working it out here. $471 meters per second. Okay. So, all right, for number 4, let's get the escape velocity. Again, that's going to be 2 times 6.67 times 10 to the negative 11th times our mass, which is 6 times 10 to the 23rd. And we'll divide that by the radius, which is 600,000. I think what I did is I came up with a planet that has 1/10 the mass of the Earth, but it's same like diameter. So when we plug this in, we'll get 2 times 6.67 times 10 to the negative 11th times 6 times 10 to the 23rd. And we'll divide that by 600,000. All right, when we square root that, I'm getting 11,550 meters per second. I'm just going to double check that one more time. So 2 times 7 times 10 to the negative 11th. Yep. Times 6 times 10 to the 23rd. Divided by 600,000. We'll square root that out. Yep, that's what I'm getting. All right, so that is the escape velocity question. And that's what I had for practice test 1. I think on the second practice quiz, which I'll work out in the next set of videos, I also have some force problems, so I'll have you take a look at those as well. So we'll work out that solution in the next set of videos.